Hello once again, and welcome to the second hour of the class. If you recall, we stopped after the definition of the errors to be traced. We had two objectives. First one is the grasping error that should be taken to zero. That's responsible from the force control side of the problem. And second one was the center of gravity. We would like to move the object the object between the actuators to be moved to a certain location, and this was our second objective. So since we had master and slave two systems, we will be able to control two objectives simultaneously in this system. Let me take this error and the position tracking error and try to write them together in a new slide. Let me go to the pen and let me select my color back again as yellow. Okay, we had the first error as E, center of gravity. Actually, we had the first one as the grasp, but we can change the order, it doesn't matter. Now, in the previous slide, we defined this as the position error. And I'd like to recall one aspect of position control. Let's go back to the review part. In the position control, we had standard position controller and we had generalized error controller, where we were defining the position control task and the position control error as a linear combination of the error of the position and velocity altogether. We will stick up with a similar scenario here, and we will be modifying the center of gravity error here, which is in the position dimension, with an appropriate one in the velocity dimension, or with an appropriate one that includes the velocity for simpler derivation. So, without loss of generality, we can define the center of gravity error as C times Q COG minus Q COG reference. That's as in position control, like what we have done here, plus Q center of gravity dot minus Q center of gravity reference dot. Now, this error, center of gravity error, is a generalized error. Is in the framework of generalized error. In a similar manner, we can define the grasp force error. Since the grasp force error naturally included the velocity component, we don't have to make any trick on this, and we can directly write that as is. So this is Ke times Qm minus Qs plus dE times the environment damping times Qm dot minus Qs dot minus F grasp ref, so grasp force reference. Once we have those two errors, the remaining part is the way or the design of the controller to move those two errors to zero value. I could have forgotten to express one detail, and it's time to express this now, that both of our systems, master system and the slave system, both of them inherently include disturbance observers. So, in the controller derivation, the only task we have to take care of is to formulate the desired accelerations for the master and the slave systems. Before we move on, can we somewhat group these errors and make a formulation for both of them? I'll here change the color. Actually, let me put a line here, and we will move to vector and matrix algebra. Well, let's continue with, let's say, this color. I like this color actually. So let's define it as a vector of errors. Sigma is equal to I can write here ECOG, E grasp as a column vector of errors, and the content of those can be written here. That is, C times QCOG was nothing but, I'm sorry, I'm just very new to this. Okay, QCOG was nothing but QM plus QS over 2 minus QCOG reference, right? I simply take this and wrote back its content from that slide. Plus, we have another component here that is QM dot plus QS dot, maybe I can put them in parentheses, that's better, over 2 minus Q dot COG reference. Okay, so we have the first line of the first row of the error column, error vector. Now we can write back here the grasp force error, directly taking this down here. This is nothing but KE times QM minus QS plus the damping side, DE times QM dot minus QS dot, and from this we're actually subtracting our grasping force reference value, right? Once we have the error, I'll again not follow the methodology we have been doing so far, and here throughout this example I would like to also show you a different approach which yields to the same result with the previous derivation. I'll have a look at something else. Let's see. If I take a derivative of the expression given in the previous slide, so if I have a look at sigma dot, what's this? It's nothing but actually this is equal to, it's now better, ECOG dot and E grasp force dot, right? The time derivatives of those two errors. If you're interested in the formula for their time derivatives, we have to go back to the previous slide. We should take this from that slide and take that and write it, differentiate them and write it in the following slide. Maybe I can put here also parentheses, actually. This is much better. Okay, so let's have a look at that and let's take it to the next slide. That is C times, we have the curly brackets, QM dot minus QS dot, is it minus? No, it's plus, I'm sorry, over 2. So remember, we were differentiating the error. Minus QCOG reference dot plus we have QM double dot plus QS double dot over 2 minus QCOG reference double dot. All right. So if we are interested in writing the force in a similar way, we can directly take this equation and differentiate and write it in the next row. This is nothing but KE times QM dot minus QS dot plus DE times QM double dot minus QS double dot minus F grasp, force, reference. Well, this differentiation is telling many things about our system, and now I'll try to highlight or express this. First question is that what happens if I assume that this derivative is equal to 0? Obviously, differentiating the term and equating it to 0 means that you have error that is steady. So your error is fixed. And the part of the controller that satisfies or that enforces zero rate of change in the error will be called the equivalent error. Equivalent controller. So we will basically benefit from this differentiation, and we will assume that the result of this differentiation is equal to 0, and we will extract from there some acceleration values. Those will be called the equivalent accelerations. These acceleration references, actually these desired accelerations, will provide the system with the ability to preserve its error wherever it is at the beginning. So we can shuffle this. Play. Okay, let me write here. Let us play with this equation. Let me try to extract information from there. I can simply write this as follows. Sigma dot is equal to, let me have the brackets here, C times Qm dot plus Qs dot over 2 minus Q center of gravity reference dot, that's the first side of the equation, and I can actually close the brackets here. Well, this is, by the way, I forgot to put this here. I'm sorry, here. And here we have Ke times Qm dot minus Qs dot minus F grasp reference dot. I think there's a forgotten item here. It's the second order derivative. Let me erase this part and add here. So minus QCOG double dot. Okay, so what I did was just taking this item and that item there, so, and this item and that item, and leaving the acceleration terms alone in another side, in the other side of the equation. Plus, I can write here this 1 over 2 here, 1 over 2 here, dE and Ke as a matrix multiplying Qm double dot Qs double dot. So that equation has the same structure with this one. It has the same items actually, but what we have done is to play with the mathematics and take part of the equation that contains the references. This is also reference, by the way, I'm sorry. So take the references on one side and take the feedback from the system on the same side. And here you have accelerations, which will be our desired accelerations at the end. So from this, actually, it's not too difficult to write that Q double dot I'm sorry, the C should go down, COG and Q double dot grasp can be defined as the right hand side of the equation. So this is 1 over 2, 1 over 2. Here you have dE, and I think I made a mistake. That shouldn't be KE, that should be minus dE, isn't it? So dEQM double dot minus dEQS double dot, this part. Yeah. And here we have minus dE at the end. So we're going to multiply this with QM double dot and QS double dot. That's just a definition. This is for simplicity. This is for ease of application. Let's make an observation. Observe that the determinant of the matrix, so I'm talking about this, is non-zero, which means that it is immutable. So while trying to extract the desired accelerations from that system, I will definitely need an inverse of that so that I can directly acquire the accelerations. Let's move further with our derivation. So by, these are simple. Okay, by setting the derivative of the error vector to zero value, what I mean is this sigma dot is equal to 0, we can extract the following equivalent accelerations. So this is Q double dot COG equivalent is equal to QCOG reference double derivative minus, so minus C times QM dot plus QS dot over 2 minus Q center of gravity reference dot. So this is nothing but, the equivalent acceleration is nothing but the acceleration reference plus C times the velocity reference. If you see that minus times minus becomes plus, minus some coefficient times the velocity feedback. But there is no convergence term here. And we can in a similar manner, we can write here Q double dot equivalent for the grasp force. So the grasping equivalent acceleration is equal to Q double dot, I'm sorry, this is F grasp reference dot, just like this, reference minus response. So minus KE times QM dot minus QS dot. Well, let's spend some time to have a look at these structures. Once again, these equivalent accelerations are very similar to the desired accelerations with certain differences. They're actually the desired accelerations without the convergence term. So if you directly go and give these accelerations to the system, you'll see that the error stays stable. So if you have some error, it will remain as is forever. It will not converge to zero value, because what we have done was simply taking a derivative and equating it to zero. That's how, sorry, let me erase this. That's how we obtained these two. Remember, sigma dot is equal to zero, right? So something, and that the derivative of something being equal to zero means zero rate of change. So the error remains constant. But with these definitions, the first order error becomes, okay, with with the operations done so far, we don't get convergence of error to zero value, right? But we rather obtain zero rate of change of error. So currently the the first order error equations are, we have these: E dot COG is equal to Q double dot. Well, oh, I think it's I can express this in a better way. Let me go back, erase this, and erase this side also. Before giving the dynamics, let me also define the convergence term, and then we will have the dynamics of the system. So what we need is, we need to add the convergence. So if you look back here, none of these equations take direct position feedback from the system. The degree, I mean, if you look at the degrees of those equations, they include the velocity feedback, the acceleration references, the equivalent accelerations, but no position feedback from the system. And without position feedback, if there is any error at the beginning, it remains as is forever. So that's what the derivation makes, actually. We will get convergence of error. I'm sorry, we don't get convergence of error, and we will get zero rate of change of error. That's why we need to add the convergence. How can we do this? Simple. Okay, try this. Simply take feedback from the system. E dot COG is equal to minus, that's minus K COG ECOG. So that's nothing but proportional feedback in the system. E dot grasp is minus K grasp times E grasp. So let's put here hint add proportional feedback over the error having zero rate of change. Well, maybe we can also express here, try adding this. Okay, so once we add the convergence terms on top of the already formulated E dot terms, we'll find this. So desired accelerations. Our desired accelerations become that Q COG desired double dot is equal to Q COG equivalent double dot minus K COG E COG and Q double dot desired grasp. So the force channel, this was the position channel and this is the force channel, becomes Q double dot equivalent grasp minus K grasp times E grasp. Well, these are not all, but I'll add two terms here. Well, let me pick a different color. Maybe this one. I hope you can see this. No, it's hard. Let me erase this and pick a different color. Okay, maybe green would be fine. So I'll say minus PCOG minus P grasp. So these are actually the uncompensated disturbances in our system. Okay, so we will assume them to go to zero with proper disturbance compensation. Well, let me say with proper use of disturbance observers. If we design our disturbance observers in such a way that it performs very nicely in compensating the disturbances, we may assume that the remaining disturbances in the system, these are the remaining disturbances, we will assume that they will go to zero. Okay? So what we are left with is just this equation. Now, if we go back to the previous slide, we already had Q double dot equivalent center of gravity, Q double dot equivalent grasp. Let's move those to the next slide. Well, we have Q double dot equivalent COG. Let me change the color back to, I think it was this one, right? Q double dot COG desired is equal to. So we have Q double dot COG equivalent. It's this reference double dot minus C times. So Q COG reference double dot minus C times we have Qm dot plus Qs dot over 2. So this is Qm dot plus Qs dot over 2. And here we have minus QCOG reference dot. So this part was from the equivalent acceleration, which keeps the error at 0 rate of change. And we need to add the convergence term minus KCOG QCOG. And QCOG was nothing but QM plus QS over 2, right? This is the desired acceleration to be given to our system. And let me write here the desired acceleration, well, Q double dot desired for the grasping activity is simply it's equivalent minus K grasp E grasp. So here F grasp ref dot F grasp reference dot minus KE times QM dot minus QS dot K environment QM dot minus QS dot, and we had minus K grasp E grasp, so minus K grasp times E grasp. What is the grasp force error? Let's go back to our original definition. E grasp was that KE QM minus QS plus DE QM dot minus QS dot minus F grasp ref. So we can write here, actually we can write here F grasp, and we can express here F grasp is nothing but KE, let's go back, it's here QMQS, that's, I'm sorry, this is not F grasp, that is E grasp. Yeah, KE QM minus QS plus DE QM dot minus QS dot minus F grasp reference. So it's the same thing actually. F grasp reference minus this minus something times this would yield to actually F grasp ref as a positive feed forward term in your equation. So let me take these. We have already formulated so these three lines, it's actually two equations. In order to fit on the screen, I had to change this here, and I also have to express this. I'm sorry for this inconvenience. This is not F at all, it's E. Yeah, it's here. Okay, you have two equations which gives you the desired accelerations in the center of gravity and grasping dimensions. So how can we move back? How can we obtain Qm double dot and Qs double dot from these equations. Here we have Q center of gravity desired. By the way, these are desired and desired. Remember the first hour, I was telling you that for systems with multiple degrees of freedom or for systems with multiple components, we will make the derivation taking into account the overall objective, which we had done so far, and we will be applying the control on each of the single degrees of freedom systems. So eventually we have to acquire master and slave side desired accelerations from these two equations. But it's not too difficult. Recall that we had this, right? So it's recall that we have, let me have a look at my notes. Okay, we have Q double dot COG and Q double dot grasp being expressed as a matrix M times QM double dot. Well, let me change the matrix from M to, let's say, omega. QM double dot QS double dot as a column vector, and use omega's inverse to get back to QM double dot and QS double dot. Of course, these are all desired values. Okay, so after all, we have finished the derivation. I'll move to the next slide and give you a block diagram. Well, block diagram of the grasping force control, well, controller. Okay, so we have two systems. Let's try to draw them here, or maybe a little bit left. Yeah, that's fine. One system here, and let's say another system maybe here. So the first system is slave system. The second one is, let's say, master. You can change the order. We'll just create a table for the signals. Just extract from here the position. You have a summation block where you add this on this, and you have here QS, QM, right? So QM plus QS, if we multiply them with 1 over 2, QM plus QS over 2 is nothing but our QCOG, right? And then we move this here. Maybe we can raise this part, raise this part also, prolong this. All right, and here we're gonna take this and this qs dot. Also, we're gonna take this and this as qm dot to two different blocks. One of them is going to create us slave side force, the other is going to create us master side force, and we have to add these forces to create tracking error. So add this and this. So, and from this, just subtract F grasp reference Similarly, we can have somewhere here QCOG reference, and we can, oh, I'm sorry, we can actually put it this way, and this is plus and minus again. So we have two controllers. Here we have the position. Well, let me write it long. Position controller, and we have the force controller. They are in separate blocks. These are nothing but our feedback with the derived gains. So your error signal goes to your position control. Your error signal here in this chapter, this side, will go to force control. And here you have 1 over 2 dE that comes from the determinant of our matrix omega. Well, your position feedback, let's put here summation blocks, and we have plus, well, maybe here, yeah, I think it's okay, and we have signal from position control and signal from force control. They're added up, given here. This is qm double dot desired, and likewise we have one signal here and another signal here, which is the second signal is subtracted from the first one, and which gives us the QS double dot desired. So that is our overall controller. I can write here, this is ECOG, that is E grasp. The grasp force error, center of gravity error, and this 1 over 2 dE comes from that omega matrix. If you look back here, just take the determinant and try to invert that. You're going to see that 1 over 2 dE comes naturally. Okay. Before I finalize the discussion in that hour, I'd like to highlight two differences, the importance of the different derivations we have made here in this class. So until now, we were enforcing certain dynamics on the error such that the error goes to zero value no matter it's no matter it has any initial value. So we were either making this E dot plus KE is equal to 0, right? And we were sometimes for the first order systems applying this E double dot plus alpha times E dot plus beta times E is equal to 0. So that was for example, velocity control and generalized error control, or for force control, assuming that you have the environment with losses, so environment with damping. That was also used for pure position control when the error is defined only in terms of the positions, and for force control when you had the environment being assumed as pure spring. Now, in the previous definition, or let me say derivation, we followed, actually, let me write here, we made use of the following approach. First, set error derivative to 0. This is E dot is equal to 0. Second, add convergence control action. So for this we had E dot is equal to minus K times E, and add the two controllers. So we had Q double dot desired is equal to Q double dot equivalent plus Q double dot convergence. And this gives us Q double dot equivalent, and this gives us Q double dot convergence. So if you look actually, that, I mean, at least in principle, this method here seems to be the same with this one. And for the particular application, we have made the derivation for the grasping for a force application. For that application, they're giving the same result and they're the same things. But this second approach has, can provide an alternative while giving this convergence action. Sometimes, rather than applying E dot is equal to minus KE, you can apply E dot is equal to mu times signum E. So you can use different convergence functions, and those different convergence functions affect the way your error converges to zero value. For example, if you use signum, then that creates a discontinuity in the convergence, and your error goes to zero value in finite time. However, here E dot plus KE, its solution is some exponentially converging curve, which is converging to zero in infinite time, theoretically. Practically, we will assume that it converges after a couple of time constants, but theoretically, it takes infinitely long to converge to zero value. Here, if you change the convergence action from minus KE to mu times signum E, so if you use the signum function, then you have a discontinuous control action in the system, which provides finite time convergence. There are mathematical proofs for that, and that part, if you change this with a signum function, it will be called sliding mode control. I'm sure that most of you have already heard about this, the sliding mode control theory, but just to give an idea of what's going on over there, I can tell you that, simply change the continuous convergence to discontinuous convergence and analyze the discontinuous boundary conditions, the discontinuous differential equations there, which provides you better convergence of error with some drawbacks like chattering and others. And that new way of deriving will be called the sliding mode control approach. So this is nothing but sliding mode control approach. I just wanted to give an idea of how the things are going over there. Well, all right. I think I filled my second hour. I will upload those videos to YouTube as you will be now watching from that link. And I want to highlight one more thing before I close. First is that, let me write here one. Let's go to some good color, maybe light green. Okay. Lecture notes will be uploaded to Blackboard. So let's say Bilgilearn. So second is that I will, oops, it was this one. I will also in Bilgilearn, you will also have the simulation block diagram and responses. So I'll upload there the simulation Simulink block diagram which I created in the school, and you'll be able to see the results, the grasping force results, along with some videos from the experiments. So first one is that I'll upload the lecture notes to Bilgilearn system, and in the same system you'll also have the simulation block diagram, simulation results, and the links for some videos, some experiment results. I was actually planning to, I mean, if that coronavirus emergency conditions were not in our life, I was actually planning to give you this demo in the class, or maybe taking you to my lab and showing it over there. But since we don't have this option currently, I'll be uploading those as recorded videos. At least you can see how the system behaves. And the third and most important item is that since the internet is not, uh, you know, we don't have a reliable internet connection. Sometimes it goes off, sometimes it's blocked, and now everyone is working from home, so that the load on the web is too high, too much. Network load is too high now. That's why I cannot record those videos simultaneously, but rather I record them offline and upload just like this one to the web. But this doesn't mean that you cannot ask anything. Just feel free to ask any question by mail. I'll also add this as an announcement to BilgiLearn. I'm readily available to answer any of your questions. You can even, make some derivation and write your question. You can, or maybe we can make some appointment for a teleconference. That's all possible. So I'm open for any kind of for any way that we can help you. Well, thanks for listening. Hoping to see you in my next video set next week. Goodbye.